So in this screencast, we'll be creating a surface mount device, or SMD component. The specific component I've chose to create is a buck boost regulator that will step up any voltage in the range from 0.8 to 5 volts to a stable 3.3 volt 200 milliamp supply. It has a standard transistor surface mount outline that is SOT235, indicating that it has a length, width corresponding to 2.3 and 5 pins. So this is the NCP14 blah blah blah. So the main difference between creating a surface mount component and a through-hole component is essentially just the PCB drawing. Instead of having a multi-layer hole in your board for each of the pins, you'll just be having a rectangle of top layer copper, which the device will just be soldered onto. So ultimately the steps will be identical to the previous video where we created a through-hole component until we get to the PCB design where it's a little bit simpler. So again, before we get started, we need some resources. So you'll want to grab the datasheet for your device and grab the pinout, the application circuit, and some drawings of the footprint dimensions or body dimensions of the part. And I've done that already. So the image at the top left here is our pinout that talks about the pin connections. So in this device we have 5 important connections: ground, an unconnected pin, an output pin, CE, and LX. Then we have a typical application circuit. So this is good because you can identify where you need to place the pins on your schematic to get the best and most concise wiring that makes for a neat design. So you want to make sure CE is at the top left and so on, so that you can match this application circuit exactly. The third thing is our soldering footprint, and we'll be using this with the PCB, and it basically just tells us where and how big our pads are going to be on the PCB footprint. So the first thing we need to do is create the component schematic. So we're going to use the pinout and application circuit to plan our drawing. So we go back to our application circuit. Our schematic component is just going to be a rectangle with 5 pins, each with a name and a number assigned, and that'll be it. It'll be quite a simple component. So let's begin by placing lines and shapes to draw the schematic. So this is our schematic library after creating our through-hole component. We're going to be adding a component now. So select the pane for components in your schematic library and select the add button. So in this case, our component name was NCP1402SN33T1G. It's a long component name. And let's set up some other properties of it. So we want to now edit the component, and we have our component properties from before. So the designator, in this case, it's an integrated chip. So typically the prefix is a U followed by a question mark. The default comment, that will be the part name, NCP1402 SN33T1G. And now we want a description so that users who are using our library can easily identify what is this component. So we know it's a boost buck regulator, and we know it's basically 3V3 volts and 200 milliamps. We don't yet have a model to add to this component, so this is everything that we'll edit for now, just basic information. So let's begin by placing the rectangle that will form the body of the component in our schematic. So to do that, we'll just go place, rectangle, and the first click will set the lower left coordinate, and the second click will set the upper right hand coordinate. So I'm going to go roughly 1, 2, 3, 4, 5 blocks down and 3 blocks across. 2, 3, 4, 5. That might be a bit too large. So I place this component here, but it's slightly off center. You'll always want your components aligned to the origin of the schematic editor, so that when you're placing it, it remains centered to the mouse cursor. So there's our rectangular component. Now all we have to add are the pins. So going back to our data sheet, we need CE, out, NC, ground, and LX in order from 1 to 5. So let's start by adding those pins in. Place, pin. We start with pin 1. We want to rename pin 1 to be the CE pin for chip enable. And you will also make sure that your crosshair is on the outside. because that crosshair is what the wire will be connected to. So we'll place our pin right there. It automatically increments to start placing pin 2. The name of pin 2 was our output. We'll place that there. And now the name of pin 3 was our non-connected pin, pin 3. And the 4th pin was our ground pin. And now we have to rotate our crosshair again, make sure it's on the outside. And our 5th and final pin was the inductor pin that we'll place there. And that's our component, completely finished. In the schematic side of things, now what we need to do is create a matching footprint that maps pins 1, 2, 3, 4, and 5 to their physical locations on the PCB. So now what we can do is create the component footprint, and the first step to do that is to understand what it will look like from the dimensional drawings in your datasheet. So this is our datasheet for the NCP 1402, and the PCB drawings are usually at the very bottom of the sheet. So here they actually give you the dimensions of the component, but more importantly in this case, they actually tell us exactly what the pad spacing and sizes will be for our surface mount pads. So we need 5 pads. Looks like they're spaced by approximately 0.95 millimeters, and their rectangular length and width looks to be 1 millimeter by 0.7 millimeters. So that's what we need to do. We need to have 5 pins matching this outline, centered about the origin. So what we need to do are place our surface mount pads with the required spacing and size, and we need to delineate that they're surface mount pads and not through-hole pads, and I'll show you how to do that. So this is our completed schematic component. We need to go to our PCB library and add in a brand new component. So the way you do that is just right-click the component space and select New Blank Component. And we'll want to actually give it a new name, so double-click the created component, and we're going to be naming this SOT235. So in this case, 23 indicates roughly the size and shape of the chip. SOT is just standard outline for a transistor, and 5 indicates that it has 5 pins. So our description will be standard transistor, standard outline, transistor, 2 by 3 with 5 pins. Very descriptive, and that makes it easy to identify which component is required. So the first thing we can do is just begin placing pads. So go to Place, Pad, and remember the same component is used to place through-hole and surface mount. So it is within the pad settings that you change between a surface mount and a through-hole pad. So press Tab, and the way that you change from a through-hole pad to a surface mount pad is via the layer option in this properties submenu. So you want to change it to be top layer, and this is the pad settings for a surface mount pad. So now what we want to change is whether the pad is round or rectangular. Typically you'll have rectangular pads, so we'll select that, and this is the area where you can delineate the size of the pads. So let's go back to our datasheet to see what the size was. We need 1 millimeter by 0.7 millimeters. So let's key that in to our device. So we want 0.7 for the horizontal and 1 millimeter for the vertical. So there's our pad of the right size. You can see the designator is actually 4. This will be our first pad, so we want it to be 1. And that is all the settings we need to modify for now. You may find it more useful to mathematically calculate what the positions will be, and then you can just enter them in programmatically, the locations of each pad here. So we've set up all of the properties for our surface mount pad. Now before we begin placing them in the document, we need to know roughly how many there will be and roughly where they will go. So let's go back to our soldering footprint. So we'll need 5 pins. From this information though, we don't know which one is which is pin 1, 2, 3, 4, 5. So we need to correspond that with our component view here. So it looks like if we were to rotate this component view 180 degrees, the upper right pin will be 1, then it goes 2, 3, then 4 in the bottom left, and 5 in the bottom right. And that's what we're going to follow now in Altium. So pin 1 will be at the top right, then 2 in the top middle, 3 in the top left, 4 in the bottom left, and 5 in the bottom right. Obviously, I haven't placed these pins exactly where they need to go. What I'm going to do is work out what the coordinates are from our data sheet and then modify those coordinates for each pin individually, just so it's exact. So let's start with pin 1. So pad 1 is the top right hand pin. We need to know how far it is from the X and Y coordinate from this origin. So if we're looking at the spacing for vertically, the difference between these two pads is 2.4 millimeters. That tells us that it is 1.2 millimeters from the origin in the Y-axis. And from the X-axis, we know that the spacing between each individual pad is 0.95 meters. So that tells us that the X coordinate is 0.95. So let's plug those values into Altium. It was 0.95 millimeters in the X and 1.2 millimeters in the Y. And that's our position for pad 1. Let's do pad 2. So pad 2 is positioned horizontally at the origin, and it's just 1.2 millimeters from the Y. So our property is X is 0 and Y is 1.2. And then we look at our third pad. The third pad has X is negative 0.95 and Y is 1.2. So you'll notice when you're in the left-hand quadrants, the X coordinate changes to a negative, and our Y coordinate remains the same because we're in the upper quadrant. Now let's look at pin 4 and pin 5. So pin 4 will be negative 1.2 and negative 0.95. And finally, pin 5 will be positive 0.95 and negative 1.2. There we have it. That's our all the pads correctly placed onto our PCB component. So again, we've placed the pads on, and essentially that's all is required for a PCB footprint. However, we do want to have a neat design, and you'll always want to overlay the outline of a component to a silkscreen layer, just so when you're soldering you know exactly which component fits where, and if there's no confusion. So what we want to do is produce a component outline on the top overlay of the silkscreen. So let's do that using Altium. So we're going to have some form of a rectangle showing how large the body is over these pads. So in order to do this, we need to know what the body size is. So we go back to our datasheet, and we'll be looking at the component dimensions here shown in the top left. We just want the dimensions of this rectangle, and they're given to us by the dimensions B, which will be the width, and A, which will be the length. And they're in this lookup table shown here. So a rectangle is going to be 3 millimeters by 1.5 millimeters, and that will be the outline of the body. So let's place that into Altium. Again, when we're placing the outline, we want it to be on the silkscreen layer, and the top silkscreen layer is named top overlay. So we can go to place, you just want the standard line, and in millimeters we want to be roughly 3 millimeters wide and 1.5 millimeters length. So I need to go to about negative 1.5, which is roughly there. We can go up a little bit. So you'll notice that my silk screen now will probably overlap with my other pads. So what I might want to do, because this line is very thick, is make that line a little bit thinner. So instead of 2.54, I might go half of that and use 127 millimeters, just so that we don't have any overlap that could produce errors on this component. So we need 3 by 1.5, so that's roughly roundabout. Now also I could just draw the silkscreen layer right over the top of my pads. The manufacturer could still produce the board. However, in Altium, if you ran a design rule check, you would see several violations of this solder to solder mask conflicts. So to prevent that and make sure that our component doesn't violate DRC errors, I'm not going to draw this rectangle completely along. I'm just going to leave lines indicating that the body stretches from here to here. And Then I will just draw in small lines where I can, indicating the outer size of the rectangle. So we haven't added much, but that still does let the whoever's soldering the board know that the outline of the transistor will be roughly that size. So one final thing you can do in this case is label which pin is pin 1. So now to designate that the top right pin is pin 1, we'll place a small circle on the top overlay right next to that pin, so we can quickly identify that. So go to place, full circle, and place it quite close to pin 1 compared to any other pin. And there we go. So when we quickly look at this drawing, we immediately know that pin 1 is in the top right, and we can solder it accordingly. So that's the end of our PCB component creation. The last step to do is to link our footprint component to our schematic component as indicated here. So what we need to do is go into the schematic and add a model and point to the model we just created. So we go to our schematic library, select our regulator component, and go down to the model menu. There's several places to do it. You can press add model here. You can double click edit the component and change the model down here, or you can go to the bottom menu in the editor and select add footprint. So what you want to do now is browse to the particular component you just created. It automatically searches our PCB library, select SO2-235, and before you add it in, you can select this pin map button on the top right, and it gives you just a mapping. So if you've named your designators a little bit differently, you'll stand out in this step. Thankfully, I've named all of mine 1, 2, 3, 4, 5, and I've made sure that they match up previously. So there we have it. Now, having done that, it's automatically tied my schematic pins to my footprint pins. And we have a fully functional component that we can use inside of Altium. So again, to test that, let's go back to our integrated library project, right-click it, and compile it from scratch. And as you can see, I now have two components. I have my through-hole component for the MOSFET and my surface mount component for our boost buck regulator. So thanks for listening. With these skills, you should hopefully be able to create any through-hole and surface mount component